In this lesson, we're going to learn how to properly interpret the definite integral for functions that change sign. In other words, for functions whose graphs are both above and below the x-axis. Now let's recall that if f of x is positive and continuous on a closed interval, then the definite integral from a to b represents the area bounded between the graph of the function and the x-axis for x between a and b. In other words, we have this graphic down here. So we see the area of the shaded region is the definite integral from a to b of f of x dx. And also notice how we have the smaller number in the lower limit and the larger number in the upper limit. So this is how we properly interpret the area bounded between the graph of f and the x-axis for x between a and b. Now, if our graph were to dip below the x-axis, then how do we interpret the definite integral? Well, here's how we do it. Now, if we have a function that's continuous on a closed interval ab, and it has a change of sign in that interval, so in other words, the graph might be above the x-axis and then it might dip below the x-axis, then the definite integral from a to b of f of x dx actually represents the sum of the signed areas, as we see below. So, to illustrate what we mean by the sum of signed areas, we have a function here going from the interval a over the interval a to b. Notice that it is positive on part of the interval and then negative on another part of the interval. And we have listed here the areas. So a1 is the area where the function is above the x-axis, and a2 is the area where the function is below the x-axis. Now, if you were to evaluate the definite integral from a to b of f of x dx using the limit of the approximating sums, the number you would get back would actually be a1 minus a2. So the definite integral doesn't give you the total area, it gives you the sum of the signed areas. So the definite integral actually treats the area where the function is below the x-axis as being negative. So that's what you would get. Now, to understand why this is, let's take a look at the next graphic. Now, to understand that, let's recall that our definite integral is the limit of our approximating sums. Remember the quantity right here, these represent the area of rectangles, and we're summing them up and then taking the limit as the number of rectangles goes to infinity, and that will give us our definite integral. Now, notice that if we look at the graphic down here, notice that where the graph is negative, when we evaluate the height of each rectangle, like right here, for example, right there might be a ci value, and then when we evaluate f of ci, well, this is going to be a negative number because the graph is below the x-axis. So this will be negative. So when we multiply f of ci times delta x, that's giving us a negative number back. And the absolute value of that negative number would be the area of this rectangle. So you see, in this summation up here, wherever our function is negative, the areas of these rectangles are actually negative areas, and we're adding them up. So where our function is positive, these areas are going to be positive. Indicate that with little pluses here. So those areas are positive. But over here, all of our areas are negative. And so we're summing them up, so you see the areas over here are canceling with the areas over here, and we can see then why in the limit as n goes to infinity, the definite integral is actually this area minus this area over here. Now, if we did want to find the total area, suppose we really wanted to find the total area, what would we do? Well, we could still do it, it would take a little bit more work. What we would have to do is we would have to find where our function is equal to 0. Now in this graphic we only have one location where our function is equal to 0. And we'd have to find where our function is positive and negative over the interval from a to b. Now in this graphic here it's positive from a to c and negative from c to b. Then we could say that the total area would actually be, we have it written down here, it would be the definite integral from a to c of f of x dx. This part right here would be a1, that would give us this area. And then this area here, this definite integral, is actually negative. It's negative a2. So notice if we go minus negative a2, that gives us a positive a2. So this is how we would evaluate the total area if we wanted it. We would have to break the integral from ab. We would have to break the integral from ab, the definite integral, into two separate integrals. One of them would be positive, and the other one would be negative. Negative of a negative number makes it positive. Or we could take the absolute value of this definite integral here. So we could write it as the integral from a to c plus the absolute value of the integral from c to b. So that's how we could find the total area if we wanted to. Let's take a look at an example. So here we want to determine graphically the definite integral from 0 to 2 pi of the sine function. Well, if we look at the graph of the sine, down here we have it. And notice that we have two areas here, a1 and a2. Now by symmetry of the sine function, the areas are the same. So the definite integral, because it adds up the sum of the signed areas, the definite integral, this will equal a1 minus a2, because the definite integral looks at this area as being a negative number. And so since a1 and a2 are equal by symmetry of the sine function, and the definite integral is then a1 minus a2, we get back 0. So if we were to evaluate this using the limit of the approximating sums, we would find that we just get back 0. So it's a lot easier to look at it graphically and determine that it's equal to 0 than actually evaluating the limit of those approximating sums. So that concludes our discussion of how to properly interpret a definite integral for functions that change sign.